So, let's go over some announcements. SCIE102, the first chapter 3 homework. Let me see if I got the email you mentioned, Ozzy. I'm not seeing an email from you. I didn't get an email from you, Ozzy, this morning. So, the first chapter 3 homework is due on the 7th. That's Monday. The next one is due a week after that, on the 14th. The quiz is on the 14th. I have finished grading exam number 1. I have that up here so you can pick up your exams. You can pick up your quizzes, chapter 2 quizzes, and the last lab as well. Here are some statistics for exam number 1. The highest score was on 97.5%, which is 146.25 out of 150, because it's out of 150. The average was around 81%. The median was at 82 point, was about 83. And yeah, there's the standard deviation there in the range. Yes. Yeah, it's up here. This pile is the exams. This pile is quiz number 2 on chapter 2. And this is a lab 3.
Oh, I'm good.
That is just going to be, that's just, yeah, so.
Yeah.
Keep it or we gotta keep it?
You can keep it. Not in any particular order. Okay. So, yes.
Okay. And Morales?
Yeah, I got it. Okay. So I'm going to continue on with chapter 3. So quick review of Newton's first law. If you have an object that is in motion, it will remain in motion in a straight line at a constant velocity unless some external force acts on it. If an object is at rest, it will remain at rest unless some external unbalanced force acts on it. Balanced forces have equal magnitude in opposite directions, and an external force is a force applied to the entire object or system from outside. So here, if you have a 10-kilogram drone moving at 4 meters per second to the east, has a downwards force from gravity of 98 newtons and an upwards force from its propeller of 98 newtons. After 30 seconds have passed, what's its velocity? So this is fairly straightforward. The forces are balanced, 98 newtons up, 98 newtons down. So because the total force is 0, the velocity will be constant. So the velocity will just be 4 meters per second to the east. Nothing has changed. It'll just keep moving at 4 meters per second to the east. The second law tells you what happens when there is some force on an object. Force is the net force, the unbalanced force, which is likely the sum of 2 or more forces, equals mass times acceleration. Mass is the mass of the system. Acceleration is the acceleration of the system. The units for force are newtons, which are kilogram meters per second squared. And this is the derived unit of force for the metric system. So in the metric system, you measure force in newtons. So here, a penny and a feather fall at the same rate in an evacuated tube. Penny has a mass of 2.5 grams, and the feather has a mass of 0.025 grams. The acceleration of gravity is 9.8 meters per second squared. What is the force on the penny, and what is the force on the feather? Okay, so you made a small mistake. You forgot to convert from grams to kilograms. It'd be you said 24 and a half for the different 0.0245. Says it's 2.5 grams is 0.002 kilograms. 0.025 grams is 0.00025 kilograms, or 2.5 times 10 to the minus 5 kilograms. So the weight of the penny ends up being 0.0245 newtons. So that rounds to 0.025 newtons. And the weight of the feather is 0.245 times 10 to the minus 4 newtons, which is 2.5 times 10 to the minus 4, or I didn't write that out. And here, if you have a 3,000 kilogram car that experiences a net force of 90,000 newtons, what's its acceleration? Remember, force equals mass times acceleration, which also means acceleration equals force over mass. 30 meters per second squared is correct, yes. So 90,000 newtons divided by 3,000 kilograms gives you 30 meters per second squared. So Newton's third law is that for every action, there's an equal and opposite reaction. If I push on something, it pushes back with an equal and opposite force. So whenever an object exerts a force on a second object, that second object exerts an equal force that's equal in size, but in the opposite direction. So action equals opposite reaction, force 1 equals minus force 2. So if those are the only forces involved, mass 1 times acceleration 1 will equal minus mass 2 times acceleration 2. You can think about it as the force of 1 on 2 equals minus the force of 2 on 1. Okay? So we're going to talk about another specific case of force, which is gravity. We've talked about gravity when we're on Earth, where the acceleration of gravity is 9.8 meters per second squared. But gravity is a fundamental force of nature. There are 4 fundamental forces of nature. They are gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. In order of strength, it's something like gravity, weak nuclear force, electromagnetism, strong nuclear force. But and in fact, the one that we understand the least is gravity. We don't know what causes gravity at some fundamental level. We can only describe it. So the law of universal gravitation is Newton's description of how gravity works. This works for moderately sized objects. When you start to get into extremes, you have to go and use general relativity to deal with and correct for things. But we're not going to do that. So the basic idea of the law of universal gravitation is that every particle in the universe attracts every other particle with a force. And the force of gravity is proportional to the masses of the 2 objects and inversely proportional to the distance between the 2 objects squared, and then there is a constant. So there is a force. It's proportional to the product of their masses between the 2 objects and inversely proportional to the square of the distance between them. So that means the bigger the mass, the stronger gravity is. And it also means the closer together the 2 objects are, the stronger gravity is. So the equation is the form G equals M1, a force of gravity equals G times M1 times M2 divided by radius squared, where G is a constant, it's the universal gravitational constant. This is capital G as opposed to little g. Capital G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And what that means is if you put in kilograms, and meters, you get out newtons. G, capital G, is a very small quantity. This is, you may notice this is like times 10 to the minus 11. The one for electricity, the similar unit for electricity is like something times 10 to the 9. About 20 orders of magnitude bigger. Though some of that are units, because the units for electricity are big. But electricity is much stronger. Electromagnetism is much stronger than gravity. It's a very, big G is a very small quantity. It's thought to be valid throughout the universe. It was measured by Cavendish about 70 years after Newton's death, with a very delicate experiment involving giant balls being attracted to each other. And it is not equal to G, little g. Lowercase g is just the acceleration due to gravity on Earth. Uppercase G is the constant for the universal gravitational constant. And it's not a force. It's a constant that lets you calculate a force. Now, like all forces, the force of gravity comes in pairs. The two particles are attracted to each other. And the reason that gravity ends up dominating on large scales is because gravity always attracts. All the other forces have both like attraction and repulsion. And so as things pile up, they cancel out. So you have lots of charges in you, but they're about an equal number of positive and negative. So you're more or less zero charge. But your mass just keeps getting bigger. And the forces that attract particles together are equal and opposite. So force 1 minus force 2, or mass 1 times acceleration 1 equals minus mass 2 times acceleration 2. So it's the same force on both objects. Now, it turns out for a sphere, if you have a ball that is consistent throughout, this is a homogeneous sphere. The actual requirement is a little less strict than that, but basically, if you have a sphere that doesn't change if you spin it, if you rotate it, you more or less have the same mass distribution. You can treat it as if all the mass was at the center of the sphere. So this actually works for like a solid sphere, but also for like a hollow ball. So for something like the Earth, you can say, okay, the Earth is basically a sphere. We can treat it like a ball and say all the mass is at the center of the Earth. So here we have two objects with masses 1 kilogram and 2 kilograms, and they're 1 meter apart. And we want to figure out the magnitude of the gravitational force between the masses. For example, the 1 kilogram mass has a force of 9.8 newtons pulling it towards the Earth. The 2 kilogram has 19.6 newtons pulling it towards the Earth. Let's figure out the force between them. Well, we plug in our numbers. 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times 1 kilogram times 2 kilograms divided by 1 meter squared. We get 1.3 times 10 to the minus 10 newtons. So the force is something like 11 orders of magnitude smaller. It's 100 trillion times smaller, something like that. So here you see the meters cancel and the kilograms cancel, and you're left with newtons. So it's much, much smaller. You can also use this formula to figure out the force of gravity on Earth. Any object is going to be attracted to the force to the Earth with a force of big G times the mass of the object times the mass of the Earth divided by the radius of the Earth squared, because we can approximate the Earth as a sphere and say that all the mass is in the center. where the mass of the Earth and the radius of Earth are the mass and radius of the Earth. But this force is just the weight, so that's mg. So mg equals big G m mass of the Earth radius over radius of the Earth squared. But these are the same mass, so we can cancel them. So the mass cancels out, and it turns out little g is just big G times the mass of the Earth over the radius of the Earth squared. So if you look those numbers up in the back of your textbook and plug them in, you'll get 9.8 or close to it. And because mass cancels out in this, the acceleration of gravity is independent of mass. So you can see the mass cancels out, so the acceleration of gravity is independent of mass. And because that's a general case, no matter where you are, if both things, that's why in space, weightlessness in space is the result of both the astronaut and the spacecraft falling to Earth at the same rate. So in the International Space Station here, let me just look it up. They're actually, this astronaut and the space station are both accelerating at about 8.7 meters per second squared. You can calculate it. Basically, the radius is about, because you're about the International Space Station is about 400 kilometers up, so you'd add about 400 to the radius, and you'll get around 8.7 instead of 9.8. So they are in fact accelerating, but the weightlessness is because the astronaut and the spacecraft are both falling towards Earth at the same rate. And you're going to experience this. You get in a box and drop the box. I would do this at a theme park in a drop ride and not in a random box that you drop, because that's a good way to break your legs when the box finally hits the ground. But if you go on one of those drop rides where they take you up high and drop you, you feel weightless for a moment. Or there's points on a roller coaster where you feel weightless. That's because you're traveling in a parabolic arc and you're both accelerating towards the Earth at the same rate. So here, let's find the gravitational force between two 1,000 ton or 1 times 10 to the 6 kilogram masses at a distance of 10 meters. Nice round numbers. So that's 1,000,000 kilograms each for mass 1 and mass 2. The distance between them, the radius, is 10 meters. And remember, G is 6.67 times 10 to the minus 11. Yeah. So you do something like, so the trick is that it helps to write it in scientific notation, but you do something like 6.67 E for the 10 to the times 10 to the minus 11 times 1 times 10 to the 6 times 1 times 10 to the 6 divided by 10 squared.
And it is not a simple.
Well, you can type it out, but it's faster to type it in as in scientific notation like that. There's a scientific notation button on most calculators. On the TIs, it's an EE button. Or you could, work out all the, you could multiply all the front numbers and then work out all the powers at the end. So this I can actually do without a calculator because the numbers are nice. We have 6.67 times 10 to the minus 11 times 1 times 10 to the 6 times 1 times 10 to the 6. So we have minus 11 times 10 to the 6 times 10 to the minus 11 times 10 to the 6 times 10 to the 6. That's minus 11 plus 6 plus 6, which is 1. So that's 10 to the 1 divided by 10 squared. That's 10 to the 2. So we're going to get 10 to the minus 1. So we'll have 6.67 minus 1, which is 0.67. 0.667. So the other thing you can do is you can always multiply all the what are the terms for the parts? So the front parts together, and then you can add or subtract the exponents. So here the moon has a mass of 7.35 times 10 to the 22 kilograms. The Earth has a mass of 5.97 times 10 to the 24 kilograms. And they're separated by 3.84 times 10 to the 8 meters. So what's the force on the moon from the Earth? Point. So this same formula, G times mass of the moon times mass of the Earth divided by the distance between them squared. So 6.67 times 10 to the minus 11 times 7.35 times 10 to the 22 kilograms times 5.97 times 10 to the 24 divided by 3.84 times 10 to the 8. That will give you 1.98 times 10 to the 20. So if you multiply all the front things, multiply 6.67 times 7.35 times 5.97 and divide by 3.84 squared, you get 19.8. And then negative 11 plus 22 is 11 plus 24 is 35 minus 8 minus 8, so minus 16. 35 minus 16 is 19. But we're at 19.8 times 10 to the 19, which is 1.98 times 10 to the 20. So that's how you could do it without using that. Or on a calculator, there will be a little button for entering things in scientific notation, so you can actually type the numbers in scientific notation. The acceleration of the moon ends up being about 0.0027 meters per second squared. Actually quite small. So if a planet has half the radius of the Earth and 1/8 of the mass, what is the acceleration due to gravity on that surface, on the surface of the planet? So remember that the acceleration of the regular G is big G times mass of Earth over radius of Earth squared. So the acceleration for this other planet would be the mass of the other planet divided by the radius of the other planet squared. So there's two factors. Cutting the radius in half will increase the acceleration due to gravity by a factor of 4 because it gets squared. But dividing the mass by 8 will decrease the acceleration due to gravity by a factor of 8 because mass is on top, 1/8. So what will happen is you'll get G on Earth is big G times mass of Earth over radius of Earth squared. G on this planet is going to be big G times 1/8 the mass of Earth over 1/2 the radius of Earth squared. If you factor out, if you get all the numbers out, that's 1/8 over 1/4, which is 4/8, which is a half. And this here is the same as G on Earth. So this will be half of G on Earth. So the acceleration will be half of G on Earth, which would be 4.9 meters per second squared. So if a planet has 3 times the radius of Earth and the same acceleration due to gravity, what's the mass of the planet? You can say this in terms of Earth's mass. Don't need the number in kilograms. So this is a similar problem. Here we want to make sure gravity stays the same. So if we triple the radius, so gravity on Earth has to equal gravity on the planet. So big G times mass of Earth over radius of Earth squared equals big G times mass of the planet over radius of the planet squared. So big G times mass of Earth over radius of Earth squared will equal big G times mass of planet over 3 times the radius of Earth squared. And if you do some algebra, the radius of Earth squareds cancel, the mass of Earth, the big G's cancel. You get mass of the Earth equals the mass of the planet over 9, or the mass of the planet is 9 times the mass of Earth. To get the same gravity with 3 times the radius, you need 9 times the mass. Basically, if you had the same mass and 3 times the radius, you'd have a 9th the gravity. But to get same, if you then want to increase the mass,
to make gravity the same, you'd need to have 9 times the mass. So another thing is buoyant force. Buoyant force is why stuff floats. Why stuff floats. The different things have different densities. And it turns out when you immerse something in a fluid, let me see if I can get a beaker and demonstrate. If you immerse something in a fluid, it will displace some water. Oh, there's a beaker here. So for example, if you put something in water, so that's it's not a very clean beaker. I'm gonna try this. Oh, okay. It doesn't have a strange resin. So the buoyant force, anything you put in water displaces some water. So if I stick this mass in the water, it pushes some of the water out of the way. It turns out you get an upward force equal to the amount of fluid you push out of the way. So that's Archimedes' principle. An object immersed in a fluid experiences a buoyant force equal to the weight of the volume of fluid displaced. And for fluids, that's both liquids and gases. So, if something has more weight than the fluid it displaces, it will sink, like so. So that ball bearing has more weight than the weight of water it displaces, because it's more dense than water. So it sinks. But if we have something that has less weight, this should have less weight, but it doesn't fit in the jar. I had a light ball around somewhere. Let's see if I have something that would work that I can demonstrate later. If something has less weight, it'll float. Because the upward force is more gravity pulling it down. Yeah, it's like a little wooden ball. Hopefully it'll float. So there, that wooden ball has less weight than the weight of the water it displaces. So it turns out the general situation you get is that if something is in a fluid, the buoyant force depends on the weight of the fluid displaced. The weight of the fluid displaced depends on the density of the fluid and the volume that's displaced. So in general, things float in substances that are more dense than them, and they sink in substances that are less dense than them. So if you're putting something in water, the wooden ball here is less dense than water, so it floats. The ball bearing is more dense than water, so it sinks. But if I were putting these in something that was more dense, like mercury, in mercury, the steel ball bearing would float because mercury is more dense than steel. And the amount, how high you float out of the water depends on the relative densities. So if you're in a fluid that is got half,
if your density is half that of your fluid, the fluid you're in, half of you will stick out of the water when you're flooded. If you're 75% of the density of the fluid, 75% of it will be water. So the denser you are, the deeper you'll flow. So if you go to somewhere with salt water, in salt water you float higher out of the water because salt water is more dense than fresh water. So you float higher in salt water because you need to displace less water to equal your weight. So if you go somewhere with a really salty water, like the Dead Sea or certain other inland seas that have extremely salty water, much saltier than seawater. I think Salt Lake might be like that. I'm not certain. You float significantly higher, and it's a really strange experience. Because many, many years ago, I once went to the Dead Sea. And it was a strange experience. And then I got something in my mouth, and that was an awful experience. Because if you thought seawater was bad to get in your mouth. So in general, ships float because they are less dense than the water they're in. So the average density of the ship is less than the water it would displace. But this also works for liquids. Oil floats on water because oil is less dense than water. Cream floats on milk because cream is less dense than milk. And by taking in or pumping out water, ships and submarines and such can adjust their buoyancy. And so submarines use this to go up and down or stay at the same level by adjusting their buoyancy. They use tanks where they pump in and pump out water. And submersibles will have weights on them that they can drop for emergency lift themselves to the surface. So if you have a ball with a mass of 250 grams and a volume of 345 cubic centimeters, it's placed in water with a density of 1 gram per milliliter. Does it float? So you can figure this out. Calculate the density of the ball. If the density of the ball is less than the density of water, it'll float. If it's more, it'll sink. So do you think this ball will float? So density is mass over volume. 250 grams divided by 345 milliliters gives us a density of about 0.725 grams per milliliter. That is less than 1 gram per milliliter. This ball will float. Here we have a rock with a density of 945 kilograms per cubic meter, and it is dropped in water with a density of 1 gram per milliliter. You think it floats? Remember, 1 gram per milliliter is 1,000 kilograms per cubic meter. So this rock has a density of 945 kilograms per cubic meter. We can do 2 things. We can convert this to grams per milliliter or grams per cubic centimeter. So that's 1,000. We multiply by 1,000 grams per kilogram, and we then multiply by 1 meter per 100 centimeters cubed, and we get that 1 gram per cubic centimeter is 1,000 kilograms per cubic meter. So we end up dividing by 1,000. The density of this rock in grams per milliliter is 0.945 grams per milliliter. So this rock will float. It is less than 1 gram per milliliter, so it floats. And if you have multiple liquids with different densities, the thing will float on liquids that it's more dense in and sink in liquids that it will float on liquids that it's less dense in and sink in liquids that it's more dense in. So if you have multiple layers, you can have something that floats in between multiple layers. So if you had like right, fresh water and like brine or salt water, and you had something that was at a density that was in between them, it would float at the border between the salt water and the fresh water. Here we have a boat. It has a mass of 1 kilogram and a volume of 5,000 cubic centimeters. If I load this boat up with 4.5 kilograms of mass, will it sink in water with a density of 1 gram per milliliter? So I'll definitely tell you the boat will float if you don't add the mass. This is a perfectly viable boat. But you put 4.5 kilograms of mass on it, will it still be able to float? That's the question. Almost, but no. So the density is the mass over the volume. So our mass is the mass of the 1 kilogram for the boat plus the 4.5 kilograms that we added, cargo, let's say, divided by the volume, 5,000 cubic centimeters. But this is in kilograms and cubic centimeters. We need it in grams and cubic centimeters. So this is 5.5 kilograms over 5,000 cubic centimeters. So that's 5,500 grams over 5,000 cubic centimeters. So this boat has a density of 1.1 grams per cubic centimeter. So it will sink. And it would even sink in seawater. But that is even denser than, that is still denser than seawater. The seawater is about 1.025 grams per cubic centimeter. So that will sink. The limit you can load this boat to is you can only add 4 kilograms to it safely. And so here we have a box, 16-gram box that has sides of 2 centimeters by 2 centimeters by 6 centimeters. That's its dimensions. If it's placed in water with a density of 1 gram per milliliter, will it float? Correct, it will float. So again, density is mass over volume. Our mass is 16 grams. Our volume is 2 centimeters times 2 centimeters times 6 centimeters. So it's 16 grams over 24 cubic centimeters, which is 0.667 grams per cubic centimeter. And in fact, if you tilted this box on its end, it would float with 4 centimeters underwater and 2 centimeters, so the long way up and down. 4 centimeters would be underwater and 2 centimeters would be above the water. Yeah, and then we'll talk about momentum next time and circular motion. So that's all I want to cover for today. Gravity and buoyancy and stuff. So
I'll see you guys next week. You can pick up your exam, your chapter 2 quiz, lab number 3, up from the front. If you haven't, I'm gonna end the meeting.